Hello and welcome to 13th lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is surface modification techniques for tribological application. We have covered several lectures, so I'm just trying to brief first what we have learned from previous lectures. We say learning from previous lectures. First thing, we have shown that most of the surfaces are rough surfaces, and we also learn the contact between tribose surface occurs solely at the asperity level. Now, even we reduce the surface roughness, still the contact will be at the asperity level. So that's why it has been written, the scale of the surface roughness is irrelevant. Contact will occur at the asperity, that's a known. If you improve the surface roughness, more contact at different asperities will occur. An extremely smooth surface we are not able to yet imagine. If it is, then the addition or coefficient of friction will increase. So we also don't want extremely smooth surface also. We require reasonable surface roughness which can give the best tribological performance. That's what we have mentioned over here. Now next one is interesting. We say the real surface area to be 2 to 4 times larger than its apparent area. Now don't get confused. This is a real surface area of a surface 1 and surface 2. Now if I say projected area will be a line, but in this case we have a complete curve, and this dimension will be 2 to 4 times. That's what has been mentioned over here, because straight line will be much smaller compared to this curve length. That's why it has been written that real surface area to be 2 to 4 times larger than its apparent surface area. Next one says that surface topography plays critical factor in determining the tribological behavior. We have already learned that surface topography is something like even different shapes, different curvature will have a different kind of tribological performances. So this has been mentioned over here, and we are saying the wear process lead to creation of the new roughness valleys, also removing the existing surface peaks. So with a time, surface roughness will improve. That is what we have learned even in lecture number 2. We have learned, and then we say that in the Bart's book, he has mentioned that before running in, these are the surface roughness parameters or RA values, and after running in, surface roughness comes down. So here are 2.3 to 1.2, 1.2 to 0.9, 0.7 to 0.6, 0.6 to 0.4. That's what has been mentioned over here. Another thing which we have learned, that the trend is going for the low viscosity. We should use a smaller or lesser viscosity compared to higher viscosity, even though this low viscosity will give us some initial high friction, but still we want to go ahead with low viscosity, because most of the time tribopair operates in this domain. So this will be a more important to consider compared to the initial phase and final phase. Now what is to be done for the initial phase and final phase? We say that we should use lubricant additives. It can be bond and the physical adsorption, it can be chemical adsorption. Those additives can be used, and then we also learn that we can use a solid lubricant, and then next lecture we also will learn that we can do a coating also. So overall we require several parameters. We require a liquid or lubricant, we require a solid lubricant, we require a physical adsorption related to additives, we also may require a coating. So that's what this has been lecture has been given. How do we modify the surfaces? We also learn another thing, that real area of contact. Now here the real area of contact, here what we have mentioned, the real surface area. So don't get confused, there is a contact area and surface area, there are two different things. And as per the Niels book, if nothing has been mentioned, then take a real area of contact as a W, the applied load, divided by hardness of the softer material by 10 times, or maybe by 10. and it says very clearly the W is in the load in Newton, hardness is in Brinell hardness or Vickers hardness. And another point comes, the real area of contact is determined by applied load. It's not by surface roughness, it's not by apparent area. The real area of contact will be decided by the applied load. You keep on increasing the load, area of contact will increase. Quite possible component may fail, but area of contact will increase. So this is what we have learned from a previous lectures. Now next thing comes, why the title of this lecture has been kept as a surface modification techniques for tribological application. Now there is a trend. The trend is that we should increase the specific load. There is a trend that we should increase the productivity, we increase the speed, and then operating temperature may also be going on a higher side. Even though we are talking about the ceramic tribology, temperature level will be very high. However, there is a decreasing trend, the lubricant viscosity is continuously decreasing. Another one, the product size is also decreasing. Now these factors are bringing tribology in a much more complex manner or complicated manner. We need to go to the nano tribology level to understand what is the impact of each factor. In addition, we do have constraints. Sustainability is coming out to be a very big constraint. Now components should not be rejected. Can we refurbish those? Can we reuse those components? And this component should not create environmental damage. So zero environmental effects. So that's why this kind of topic is very essential. How do we modify the surfaces which can be a sustainable, can be used for the number of years, and then it should not create a more wear or maybe say almost zero wear. So these are the important aspects. Now little more difficulty comes particularly with the piston ring lubrication. We have learned that coefficient of friction varies with a Sommerfeld number. Now in this different kind of a figure has been shown, an x-axis is a specific film thickness. There is a lambda ratio. Lambda can be capital or small, and mention that the effective film thickness by surface roughness. It can be composite surface roughness. So what is the interesting thing comes over here, piston ring lubrication, it experiences the boundary lubrication, it experiences mixed lubrication, it experiences EHL, and it experiences the full film lubrication in one cycle. So if I want to optimize, what do I do? Because if I have to optimize a lubrication condition for boundary lubrication, I have one technique. I had to optimize for the mixed lubrication with some sort of already knowledge, available knowledge, then I can optimize. For EHL, optimization will be different, but in one cycle whole thing comes, that naturally we really cannot handle solely on the lubricant level. That's why we really require a surface modification. And I picked up this figure from the one publication which was published in 2000 by Priest and Taylor, and then what they mention also in their paper, the designer encounters challenges in using same lubricant. In interesting thing, IC engine we use the same lubricant. Now that lubricant will be used for piston ring, will be used for the cam and follower, will be used for engine bearing. So several different components will be utilizing the same component, the same lubricant. That means if I have to optimize the condition, I have to go to the local level, and local level means individual component level. Individual component level means either we go hard with the coating of that component or providing some sort of a localized surface modification. That's why that is in this topic is important. So what we can write in this manner, the decreasing oil film thickness between the tribo surface make surface topography or topography and surface profile more important in deciding how well they will operate in terms of the friction and wear. So this is a very important. We earlier consider only lubrication. Now we are switching over to the surfaces, surface topography also. Even though we know specific film thickness includes a composite surface roughness. We already mentioned here specific film thickness we already consider when we are dividing into the subdomains like what will be the boundary lubrication, mixed lubrication, or maybe EHCl and a hydrodynamic lubrication from that point of view. But we may require to include a real surface roughness also. That becomes a very important for us to consider. So few things I'm showing here. This is the surface texture and form of the protrusions. This is the surface texture in time and the form of the dimples. Both the surface texturing or surface modification technique have been utilized. This is also the surface modification of the ring where they are using cast iron or steel surface on the material as substrate, then nitriding layer, chrome layer and PVD layer. So they are using a multifunctional layers or multifunctional coating, and coating thickness may be few nanometer to few microns. So we are requiring more and more close manufacturing. So from design to we shifting to the manufacturing, and we really require a manufacturing excellence to get this kind of results. Otherwise, we will not be able to get a good results. Now, again, referring to one table of the Priest and Taylor's in the publication, they compare what will be the this parameter in engine bearing, what will be the parameter in a piston ring liner, what will be the parameter in cam and follower. You can see here the minimum film thickness in engine bearing is lesser than 1 micron. Piston ring it comes to the 0.2 micron, and then cam and follower it is further down the 0.1 micron. Maximum temperature which engine bearing experience is a 180 degree. That means again conditions are going on a severe side. And then comes to the piston ring, again liner interface it will be 120 degree, and within the groove where this rings are placed is around 200 degree. Cam and follower contact temperature may be 150 degree. Coming to the specific load or more specific term, the maximum pressure is a 60 megapascal, piston ring is 70 megapascal, while cam and follower is a 600 megapascal. One more interesting thing comes over here is the shear rate. You can see the shear rate in engine bearing is very high, 10:8, very high. Almost all the lubricant will go through shear thinning effect. Piston ring is 10:7, and the same thing can follow 10:7. Now, what is really the minimum viscosity which we really require for engine bearing? It's around 2.5 millipascal second. While what we require oil that should be little more viscous compared to the bearing lubricant, we require a 6.5 millipascal second. Now the same lubricant has to serve to the piston ring lubrication, same lubricant has to serve the engine bearing, but we really require a different kind of lubricant oil for this purpose. So how do we really come up with the right combination? Another thing which comes engine bearing surface roughness, they are keeping around 0.3 micron, while coming to the piston ring 0.2 micron, and cam and follower 0.3 micron. Now this of course I'm assuming that these are the 23 years back values. Now it has come down much smaller values compared to this, because continuously improving the manufacturing process. And then what this paper also mentioned, that piston ring, which as I mentioned earlier, the cast iron ring or steel, whatever the surface subsurface we use, they go through the surface treatment or coating on outer edge. This is outer edge which we are showing, and occasionally on side. So in the side also there's a possibility, if we find that there is a possibility of the coefficient of friction or the wear rate, we can do a coating, or maybe the surface treatment, or maybe we keep homogenization kind of thing, so then we can do a treatment. Otherwise wear rate will occur only on the outside side. While instead of this material, if the ring are made of the cast iron, and then we are able to bring the spherical graphite or the surface, or maybe we can do a coating, or maybe we can say the graphite, and on the top of that molybdenum coating can be done by various method. Of course, in this case one method has been mentioned as a flame spraying. So that's one of the method of doing the coating of molybdenum on the steel or cast iron that has been shown. And more thing is that they are changing the shape also. It's a barrel shape. convex shape profile and with a deep drop. And that we are able to also see that when this piston ring lubrication is operated at the 0 hour, we are able to see surface roughness, and after 120 hours we are able to see the surface roughness. The most of the peaks have been trimmed in this case. That means running in really helps. While the peaks valleys are more or less same, in this case it is not really changing a lot. So what we are saying, after running in piston ring we are getting better in a surface. The peaks are removed and valleys are remaining, so it will cause a negative skewness, and a negative skewness of the tripod surface is preferable. So what we can try to give in some sort of mechanism, we say when subjected to load, plastic deformation of the surfaces will occur. So whatever this asperities which we are saying that has been trimmed, it may be because of the plastic deformation, and then when a load is removed, what we call is a brinelling is remaining, or the plastic deformation remains, it changes the surfaces, right, and that causes a real surface area to increase. That means after running in, real surface area of contact increases, pressure comes down, wear out may come down also. So, and again we can say here the running in results in a generation of smoother surfaces characterized by the decrease in the surface roughness. If we are able to do in situ operation or if in situ measurement, we will find the surface roughness has improved, but it is not always. If contact conditions are not favorable, surface roughness may increase also. Maybe 90-95% we can say after running in, surface roughness has got improved, but quite possible in some cases the surface roughness may get worse also. Quite possible initial surface roughness we are keeping 0.2 micron, and after few hundred hours operation it becomes a 0.5 micron also. Well, we can say more or less running in really helps, improves the surface quality, increase the conformity between the surfaces, adjustability between the surfaces, and it will be really helpful to us. Now, this is another example coming from the same paper, Priest and Taylor. What we are saying here, the cam when runs, it has a three profiles or three different profiles. One is a circular profile, another was a flank, and last one is a nose. And they have tested the surface roughness. Then we are able to see, particularly for the nose case, whatever you do, surfaces are getting worse. So, zero point 0.2 initial and the 0.2 micron initial RA value, after 100 operation, or it becomes a 0.5. 0.31 becomes a 0.22 is improved, 0.28 the 0.17 is improved, while 0.252 it has changed, 0.96 it has changed to 0.34. So here the surface roughness, initial surface roughness is not really mattering a lot. Conditions are changing, sometimes increasing, sometimes decreasing. So that's why we say we don't have any firm theory which can give all the good results. That's why we require experiments to be performed, and based on the experiments we get a data, and those data should be analyzed with our experiential learning and theoretical finding. And that's why we really require some sort of regression analysis whenever we do experiments, do noise removal, and then we can use some sort of a regression analysis, maybe using some equation. It can be linear regression, it can be non-linear regression. We can use this kind of regression equation, kind of the curve fit method, and then if we are able to really utilize this in a much more general manner, we also add one error term, and we try to optimize the result by minimizing the errors. So this is what we are supposed to do in this situation, particularly when we are saying the cam follower mechanism. You can see surface roughness in the base circle is not more changing significantly. Coming to the flank also is not changing significantly or even marginally also. So the surface roughnesses are remaining more or less same. So it's not necessary every surface gets improved. While in this case we are saying the flank remains same, base circle remains same, but nose is getting rougher. That's why we say that tested against a follower for duration of 100 hours, and of course we are doing some sort of induction hardening, so surface treatment, so that the hardness up to depth of the 2.5 mm is there. Surface of hardness may be even 60 plus HRC. And then it has been also, all the things have been done. It is not that because of the manufacturing of the cam was bad, that's why it has happened. They are writing very clearly, stresses were relieved, and then proper grinding was done, and then phosphating also was done, so that lubrication properties can be imparted to the cam follower mechanism or cam mechanism. So we say minimum alteration in a roughness on the cam flank and over base circle was observed, but came become rougher at the nose regardless of initial roughness. So this is important to consider. Same everything, same on the complete cam follower mechanism. They have it, the cam has a 3-section base circle related, because the load is not changing significantly, remains same. Flying also more or less remains same, but nose, which is subjected to very high stresses, the surface roughness is changing. Sometimes it is increasing, sometimes it is decreasing. So which surface roughness should be kept so that we get a best result? It is a really difficult to understand without doing really experiments, or experiment in presence of all the real factors, like a real lubricant, real system, actual the cases, to get the overall results. Of course, when we say regression analysis, we will be discussing more in 23rd lecture onward. We use R square factor, which is a coefficient of determination, and we say that whatever we are trying to fit, the R square value should be greater than 0.9, and R square value is calculated based on errors. The lesser and lesser error, the better and better the curve which we will be getting. Once we get a curve, we can optimize, we can really do some sort of improved manufacturing, so the overall results are favorable. So we really require this kind of regression analysis equations or relations. Now we have understood that there is a need of surface modification to accommodate the various condition. As I say, the lubricant alone cannot handle all the conditions. So really we require more even surface treatment, increase in hardness, providing some sort of coating on the surface. Of course, coating will be learning in the next lecture, the lecture 14, which will be discussed only on a coating. Now here already we say the tribo components to be a more optimal balance. So we really required mechanical properties, which is a bulk properties, and we required surface qualities also. And so you say the surface design is a process of manipulating surface texture. When I'm using the word surface texture, doesn't mean only one thing. It is also it can really add some sort of retention of the oil on the surface. So it is really providing some sort of lubricant properties, so that friction can be reduced, wear can be reduced. To generate a desirable surface parameters to reduce a surface failure due to wear, it can be erosion or abrasion also. Another thing is that why we require surface modification, we say that we many times we want to improve the surface roughness, so that we obtain more or less EHL or hydrodynamic lubrication. Even in staff lubrication, even in smaller lubricant, the quantity of the lubricant is available, there's no recirculation. So in those situations also we can should get a EHL, hydrodynamic lubrication, replacing completely boundary lubrication, because we know the boundary lubrication is on slightly higher friction and higher wear rate. So if you want to control or keep a control on the friction and wear, we should eliminate the boundary lubrication and bring that to the EHL case, if maybe to some extent the hydrodynamic lubrication also. To improve the surface property, and we really require to do a surface treatment to increase the hardness, apply coating or doing some sort of plating to increase the hardness. If hardness increases, and there is a chances the wear resistance also will increase. Not only this, and if we are doing some sort of passivation, even the corrosion resistance also will increase. And this kind of measure have been applied to a number of components. Let's take example of spur gear, cam, follower, and then this was already discussed that in lecture 11, that if they have a more EHL case, particularly because of the low geometrical conformity, it will really give a good results. Reason being, they have a small contact area and that creates a high contact pressure, and because of that, if there are the hard surfaces, that will give a really the good overall results. If it is elastic, more elastic surfaces, then they deform, will provide a good result from the conformity point of view or from a friction point of view, but sliding ratio will increase. If the sliding ratio is increasing, then there is a possibility that area of contact will increase or contact width increases. Then whatever the validation which we really required EHL will not be satisfied. So that's why we really require a harder surfaces. That too on both the components, is not only one component, because if so one surface is very hard compared to other surfaces, naturally abrasion resistance will increase or abrasion resistance will come down and abrasion chances will increase. So we require surface hardening. It can be done by induction hardening method, it can be done by flame hardening method, it can be done by laser hardening method, or shot peening also can be utilized, which also give a good surface texture. So the overall we are able to get a EHL condition, and then reduce the chances of wear rate or scuffing or getting adhesion between the two surfaces. One more important thing in these days is coming the heat transfer capacity. If thermal conductivity of the surface is on higher side, temperature will not rise to significant level, and then friction and wear will be well within a controllable limit. If friction temperature increases, naturally the lubricant which has been utilized, it will degrade. If it degrades, the friction will increase and wear rate will increase. So for that purpose, we really require to enhance the heat transfer rate of the surfaces. One more thing in these days has been discussed is the wettability of the surface. We can understand wettability from a water point of view, says that the hydrophobic material and the hydrophilic material. In case of the hydrophilic material, what is happening, the water gets sprayed on the surface, that is spreadability is there or wettability is there. While coming to the this non-wettability or limited wettability, that molecule of the water will remain on the surface, a drop of the surface will remain on the drop of the water will remain on the surface, it will not spread. In the situation, coefficient of friction will be lower in case of hydrophobic surface. Now coming to the oil, if the surface is not getting wettable or drop of the oil remains on the surface for the longer time, naturally the availability of that lubricant will reduce the coefficient of friction. And that has been mentioned over here. Steel completely weighted, because steel wettability is much a hard side compared to DLC coating, which we'll be discussing in the next lecture, which is a DLC is a non-fully wetted surface, and then friction of a non-fully wetted surface decreases substantially. So if you want to decrease the coefficient of friction, we can really provide some properties to the surface so that lubricant doesn't get sprayed on the surface, it remains on the kind of the droplets, and it will reduce the coefficient of friction. And that's what has been mentioned, to impart a hydrophobic characteristic on a surface that slides. Hydrophobic surfaces possess properties that resist the weighting, resulting in a significant reduction in the friction value when the fluid flow over them, or maybe say it doesn't get sprayed, so it doesn't get squeezed out also. One more thing comes, whatever the treatment or surface modification or treatment we have been mentioning, is it really applicable to all the material surfaces? Quite possible. For plastic we required a separate treatment, for composite we required a separate treatment, for metal we required separate treatment. So you need to really understand. However, in the present course we are not going to discuss all the method, we have kept only one lecture, so that I can give you overview, and then if there somebody is interested, they can get into the manufacturing of those aspects, or maybe say those surfaces or treatment, and then get a more depth. So in this lecture we are just giving a kind of overview of the surface modification techniques. Now I'm referring here the Niels handbook, which has given table 27 particularly on the surface treatment of the ferrous material. And you can see here that first the thing is the induction hardening of medium carbon steel. Second is a flame hardening of the medium carbon steel. Third one is a laser hardening of the medium carbon steel. And as I mentioned one more, there's a short pinning of the ferrous material. The short pinning in the treatment pinning is kind of changing the surface texture also. Coming to the induction hardening, we can get a something like a 61 HRC hardness up to a depth of the 5 mm. And this is particularly important because in the lecture 4 we understood under the contact stresses and the sliding direction, the maximum shear will occur between and below the surface. Now, if this below surface is a 1 mm or maybe say 2 mm, then this kind of treatment will be very important. Otherwise, the surface will suddenly get delaminated and substrate will be exposed. Coming to the flame hardening, which gives a laser hardness and laser thickness also. So we need to see which one will be more useful. Laser is a very high hardness, something like more than 66 HRC, but depth is only 0.75 mm. So it depends now. If I do analysis and find that maximum depth of the stress is coming only 0.25 or maybe 250 micron below the surface, I may go hard with the laser beam related heat treatment or laser hardening treatment, because it is instantaneous and the hardness is very high. It will may be very good solution. It may provide a good solution for us. However, if the surface texturing is a more important, and then that it can possible up to 500 micron, we can go ahead with the short pinning, because most of the materials after as a finishing operation, short pinning is done on the surfaces also. So the localized heat treatment with the texturing happens on the surface, and that what we use a work hardness of the surfaces, and because of the short pinning method. We also come across another the treatment what from a sustainability point of view, we say the surfaces may worn out, but can they be reconditioned? And then again, this Niels handbook provides a table 17.1. We say that there is a possibility of the resurfacing, and then the doing appropriate conditioning of the surfaces, and after that doing a coating, or even removing the surface and the damaged surface and giving some sort of initial treatment so that coating can be deposited on the surface. So a lot of methods are available in literature, and over the last 30 years there are a number of ways to we say that reuse the worn surface. Do not throw the surface and the material. It can be reconditioned and can be more useful. And if technology is not there, then we have a various method to really do the right treatment. And well deposition method is one of the well known, that even the removal of the 1 mm, and we do a 1 mm to 3 mm deposition is possible. It can be powder form also, or it can be thermal spraying, or it can be electroplating. Electroplating can be discussed in the lecture 14, which will be the kind of the coating for us. And then what we are saying here, then the factors that we need to really keep in mind: what are the dimension, what is the configuration of the component, because the coating or treatment will be depending on what is the overall volume, and what is the surface, and what kind of features we need to really impart, which really give a right condition. Is a gear or gear, naturally we need to do a surface treatment according to that. So that's what has been mentioned here. And finally, finishing also required. So quite possible that this repair of the worn surfaces will be much lesser costly compared to the new component. So one thing, it is a cost is a beneficial side. Other one is a sustainability. We are not going to use a new raw material. We are not going to we say that process the raw material to come to bring to this material, or maybe the component which we really require. So these are very important. And of course, Neil also has in the Neil's book also they have mentioned a number of technique. And of course, the majority of technique are the welding and spring. And then they also have mentioned what is the complexity level, what is the level of the skill requirement. They also have given the rating 1 to 4. 1 to 4, that means if I want to optimize, I can use algorithm and then I incorporate these values, and then I can choose whether material or whatever the manufacturing process which is required. It can be the gas welding, it can be TIG welding, it can be MIG welding, based on this data. And of course, if the data have been changed, we can incorporate those new data, new research data into this, and then can go ahead with a real right selection of the process which will be required to improve the surface, or particularly by the refurbishing the surfaces. So these are available literature, and we should really learn this and try to implement so that we are getting better results. Now, in this case, number of methods are there, but this method we say that metal arc welding is applicable for a wide range of material. The TIG welding is applicable for the range of material, and then coming to the plasma spring is available for the most of the alloys and ceramic materials, and then we use powder to the deposit on the surface. So, manufacturing processes which are widely used for the several materials, naturally you using those machine will be much easily available. Now coming to the surface texturing, which we have already discussed couple of times in the present lecture. We what we are trying to do in this case, we say that we don't want any sharp peak. So even the aspirated top should be rounded. If the rounded angle is around 160, 150 degree, then the damage to the other surface will not be substantial. Second, when the surfaces are there and there are pockets, in this case of valleys, it can really allow us to store the debris, because even the debris which is getting generated at the interface, it can be dumped in this case as a debris pocket, or maybe say this surface can act as a dustbin, and it will be overall useful. And then last maybe say 1 decade, people have done a lot of work on the surface texturing. So in these maybe say next 4-5 slide will be exclusively working or discussing only on surface texturing, which is surface modification technique. Surface texturing itself is a surface modification technique to create various micron to nanoscale pattern on the contact surfaces. Now these are some example. We say honing of the cylinder liner is a surface texturing. Texturing of the magnetic storage device and MAM devices, this has already been implemented. Reason here is that to reduce adhesion, as I mentioned earlier, the extra smooth surfaces will increase adhesion, and restriction will be a problem. So did you want to reduce, then actually the area of contact need to be reduced. Even in mechanical seal, many times the gas gets entrapped, or maybe the liquid gets entrapped in because of the this kind of peaks and valleys around it, the peaks and the deep valleys. Then it provides extra sealing, so that's very important. So what we are saying, the surfaces must be engineered to retain adequate amount of the lubricant. So we are keeping kind of the pocket where the lubrication is there, ensuring consistent supply between the sliding components. So it is a storing lubricant and giving during the sliding condition. Microscopic features, something like indentation, furrows, cavities, or maybe say some sort of in the valleys, they are able to trap the debris, even keep a lubricant there and disperse the lubricant. So that's why we say regulated surface softness to hold onto the lubricant and prevent direct metal to metal contact in the transient condition is really required, and that can be done by the surface texturing. So that's why the surface texturing is really getting more popular. Now what is this surface texturing? We say it can be a simple dimple texture to more generic. We will show you the different kind of textures which people have tried. Of course, in this case, we don't use the conventional manufacturing. We use mostly the non-conventional manufacturing processes. It can be chemical etching, and we will explain in next slide. It can be short blasting, short painting kind of thing. Iron beam etching, photolithography, laser texturing. This is one of the very important technique which people have used extensively, because there is a localized effect and it doesn't give a really very high stress level. Of course, it gives a rougher surface, and then again the finishing needs to be done. There are the few more important thing is abrasive jet is also getting popular, or maybe the abrasive water jet machines. These all are the non-conventional manufacturing machines. So question comes, instead of going for the super finished operation, can I go ahead with the laser texturing? And if we are able to do that, will really help the tribological surfaces, will really reduce the friction and reduce the wear. Now, what are these techniques they are doing? They try to remove the material from surface, or because of the short pinning kind of method, they don't remove the material, they display the material. So maybe material from this pocket has been shifted to this side. So we get a peaks and valleys because of that, or maybe there is a possibility of the self-forming procedure. Now, if I say running in method use nicely, then it is basically self forming process which can be achieved this using that method. Now, why we are saying that we really require a non-conventional machine, reason being the mechanical machining technique is like we take a example of milling, turning, grinding, even the sandblasting. They can produce a pattern which we require, they can produce even a pattern something like this, but it is only on a large scale texture, and then they cannot be precisely controlled. But when we are saying the surface texturing, it needs to be precisely controlled, otherwise we will not get desirable results. Now this is what we are mentioning here. So either we go ahead with the texturing something like a protrusion like this, or maybe valley creation something like this can be possible. So we say in tribology effect of the micro dimple organized in this is the array kind of thing. We are saying maybe 1 2 3, and you can see the array arrangement has been shown here, has been organized in arrays on a piston ring and thrust bearing. There are a number of publications which indicate that when they have done on the piston ring and the bearings, they have shown the reduced coefficient of friction, wear and increased service life. And they say that texturing does a three roles or plays three role. One is that they incorporate the lubricant as a reservoir, and they trap the debris, and then they also one more thing, they work as a micro bearing. So one bearing may have a number of bearing, one gear tooth may have 100 bearings. So they are the nano level or the micron level, they work a slightly different manner, they have a load carrying capacity also. Coming to the chemical etching, what we do, we selectively remove the material. That means we want to remove this kind of material from here, material from here. So this is selectively removal of the material from surfaces using the chemical agent. Of course, the pattern and texture can be generated based on the what kind of whether we want a material rate removal rate because of the corrosion or because of some displacement that need to be done, and it will depend on completely on the composition and concentration of etchant which we are using. However, it has been mentioned very clearly, they have a good precision and repeatability. So compared to other method, this chemical etching is one of the well known method. As I mentioned, laser texturing is a very good method, and then next comes the chemical etching method. Now, as in this case, you are able to see that we are depositing some material. The question arises, why not we do go ahead with the 3D printing machines and print the whatever we really require. And I believe that this is the future, because most of the products, if they have been getting manufactured by 3D printing, then in the situation we can really generate the specific pattern or texture, because it is only the three-dimensional printing and with the completely digitization. So we can create a really more complex features, and whatever the customized feature what we are able to make use of the software, and then we are able to optimize that. Laser ablation as the most popular technique, we say that it removes the material to produce a texture using concentrated laser, and then this laser intensity needs to be adjusted to what kind of pattern we really require, what kind of the depth we really require. And that's why if the more the depth, naturally we need to increase the power. If the laser depth, we need to reduce the power to create a micro and nano scale the texture. And then this method can be used. This method can be utilized for the several materials. So that's why we say that laser ablation is the most popular method and widely used for the laser texturing purposes. However, it's costly also. Now, one more thing is coming. We learned from in the last lecture solid lubricants or solid lubrication, and then here in this case we are learning something like a surface texturing. We say that solid lubricant requires a retention, so they really require some sort of bucket. Texturing really require to make a surface in a manner which can provide a space for the lubricant to be getting stored, and the bucket where this debris can be stored also or for time being. So these two together can be done by integration. So that's why the now recent time we are going ahead with the integration of surface texturing and the solid lubricant. We say the superior characteristics of such as the efficiency, precision, dependability and longevity have been achieved in the case of gears, tools, seals, fluid film, lubricant bearing, rolling contact bearing, artificial joints, and it has a several advantages people have started using, and they are getting very good results. Now, why more emphasis for the disintegration? We say surface texturing may increase the stress concentration because we are creating several features, several kind of the holes, and because of the irregularity or maybe the discontinuity in material, stress concentration will increase. To some extent, mechanical strength also we may reduce. Reason being, there may be some possibility of the crack and will be, and the under fatigue loading will increase in size. And we say low capacity, load carrying capacity. Now, this load carrying capacity because we are removing the material. One more thing comes, many times when we come to the corrosion, and if there is a water or maybe say electrolyte, they get into ingress into the this kind of textured surface or pockets, and they make electrolyte cell, and that creates a more and more corrosion. So if the solid lubricants are filling those thing, all the valleys, that overall will give a good results. So that's why I say we can get a desirable material tribological characteristics by combining surface texturing with a solid lubricant coating or solid lubricant itself. Material with improved anti-friction and wear resistance characteristics to solve the mechanical strength and material lubrication performance. So I can get a both win-win solution. Still keep a mechanical strength intact without really reducing the mechanical strength, and then we also get this kind of lubrication performance. So we are getting both the things. So that's why I say the surface texture can be used to embed the lubricant. Now people have tried with the graphite, MOS2, PTFE. This minimize the contact area, which is because if there are valleys and peaks have been term or maybe have been textured in a manner, they really give a kind of rolling action, a gliding action, and the lubricant also comes into picture, which is not really the material to material contact. They will have a low shear strength, or maybe say liquid lubricant, or maybe say even solid lubricant will have a very low shear stress. Naturally, it will be really helping, it will improve the lubrication retention, and then ensure the steady supply of the lubricant whenever there's a need. So this is the overall win-win situation, and that's why we require integration. However, whenever we do integration, there are some guidelines. We say that there should be sufficient separation between texture, otherwise stress factors will come. Another thing is that the depth or maybe size of the texture should be made in a manner so that whatever the debris are getting generated, they are able to get trapped in those kind of pockets. Pockets should not be too small to not to really catch debris. If it is a very big, naturally it will be a compromise on the material strength. So this kind of optimization constraint is really coming into picture whenever we go this the texturing plus solid lubricant. We really require a good optimization, and then it is really and then reduce the overall wear, and then if the particles are not there, then the three body abrasion will not be there, so it will reduce incidence of the flowing also. One more thing is that the different load condition people have said what is area coverage. Some people say that This texture should be around 10% of overall area. Some people say 11%, some people say 15%. So now it is very important to analyze what will be the overall percentage, and I have not seen more than 16% coverage. So that will be, we say, maybe say 10 to 16% area coverage. Coming to the depth, often we say the shallow texture will be better, because if the in a deep case lubricant is occupied, it will not come out like a deep well. If there's a shallow well, naturally lubricant will remain and immediately can be utilized whenever there's a sliding conditions. So those conditions are important, and of course it should not have residual stresses. When we fill a lubricant in that, more or less residual stresses will be lesser compared to the without lubricant. So this is important. Now coming to the this texturing process, first we are talking about the laser beam texturing. Now again, laser beam texturing we are dividing in two subclasses: pyrolytic and photoelectric. And we say the pyrolytic where really the temperature is on the higher side, and while coming to the photoelectric, the temperature is on lower side, and where the chemical reaction really happens. And sometimes we use a word, it is a cold ablation also. And here it has been shown that titanium sapphire laser has been projected using the focus lens, and then it really melts some material at the localized level. So really we really require some CNC machine or computer controlled on the place where this specimen has been capped, and they travel and as per the requirement. So we really require the computational method to really move the surface in a manner so we get a desirable finish. However, the one of the major issue with the laser texturing is that heat affected zones, and some places particularly where there is a discontinuity comes. So there is a valley and there is a smooth surface. In between there will be some sort of discontinuity. There the bursts and the bulges will be there, and then that is going to really give a more problem. That's why we say that after laser texturing, the super finish operation should be done. It can be grinding, it can be polishing, it can be lapping. That needs to be accounted properly. Now we say the technique used for the laser projection. As I mentioned earlier, we really require CNC machines also, and then to reduce the heat generation, they also use a femtosecond method with the laser is being generated only for a very low time, and then again it started. So they go ahead with the nanosecond pulses, which gives a better fabrication control way, and then it really offers the very good services, because it can be utilized for the different features, different shapes. As I mentioned, that if we want a more deeper, we need to require a more laser power. If because a shallow depth, we'll require a separate thing. So it can be really customized whatever we want, whichever method we want, we can go ahead. Even we can go with several shapes on one surface, or shape inside another shape, or maybe say nested shape we can also can achieve using the laser jet. So we have a more versatility using this kind of manufacturing process. And this is another process has been shown, what we call a micro slurry jet processing. What they do, use a ceramic material, and then the polyamide taps on that, and then initially using the laser they try to make a what will be the mask. So they design a mask using the laser, and after that they use the micro slurry jet to really cut the surfaces properly, and that is where we really require a real finishing. So if it is this slurry is removing this surface, we are getting this, again removing this, so there is a mask, and then and on the mask we don't impinge the micro slurry jet, and then we get a shape as per this manner. However, again we say that making a mask itself is cumbersome, and then quite possible we are requiring instead of one process or two processes. So it may not give much better results compared to the what we are getting from a laser. Of course, and the heat affected zones will be lesser. Now depends on the what we really require, then only the appropriate method can be selected. So this is the second method to make and then the texturing. Third method is basically ultrasonic machining. You can see here that we vibrate this complete tool at the high frequency, which is more than 20 kilohertz. We impinge in the abrasive materials, and because of the high frequency vibration abrasive material, substrate will be losing some material and will be getting a desirable shape. Again, it can be customized the way we want. Of course, this complete as figure has been given to show how overall process works. And then the tool motion in vertical direction and abrasive material can be has been shown in this manner. However, we say that this kind of a machining is more suitable particularly for ceramic material or brittle materials, and we have a glass, silicon, so on, we can be utilized for this purpose. This we have a lot of method with a precision in this case we can use circular, we can use a circular, rectangular, hemispherical, different shapes with varying dimension, even up to the few mm. We have a versatility in this case. And now only thing is that we again and again we really required some sort of motion of the specimen, and we really required a CNC machine kind of fabrication system, which will be again a costlier. So all this surface texturing are a bit costlier because we really required a with good control on a specimen movement, whichever direction we want, whichever place we want. So that should be customized. In one go we don't get all the textures. Maybe when we go for the short pinning method, then is possible, but when we go for the laser jet or maybe abrasive jet machines, we will not be getting we will be getting one by one, not a one time altogether. Last one in this case is electrochemical machining. You can see here the substrate material we use a dry, and then again first the mask is made, and based on the mask then selective removal of the material be utilized. We say remove material through basically the using corrosive action or anodic dissolution. We use electrolysis process, and then in this case we can use some sort of electrode which can gives a replica of the shape also. So that sometimes when we go much more control side, we say we can do a scanning tunneling microscope technique in conjunction with electron cyclotron microscopy, which is again turning out to be very costly process, but we will can get up to the nano level, nano groove dimension. So if we really require very sophistication, we can use this method. And then but we say that the ECM can be superior compared to other textile manufacturing machines, reason being that it has a high efficiency compared to other, and heat effector zones will be lesser, and then running cost overall is lesser, but initial cost may be also on a higher side. So this chemical and electrochemical machining will be useful if we have many more pieces to be done simultaneously. Now this is what has been shown here. In this case we say that there are two processes, one is with a mask, another one is a without mask. We have shown the mask, and that what we are saying that cost factor is a mask one. Without mask it will be little more costlier. Now what are the different shapes which you use for the this laser texture? You can see the shape 1, shape 2, shape 3, shape 4, shape 5. There are many. Again we are saying that are discrete and continuous. So all these are the discrete shape, while in this case we are getting continuous one. The next question comes, so why do I go with the texturing? Why not we go with a simple grinding machine, and then I can get this kind of a texture. So this surface roughness optimization also can be done using this one. However, we know this kind of texture will not be useful unless we block this portion and this portion. If we block, then only the lubricant will be retained, other will be completely drained out, so will not be very useful in the situation. Again, as I mentioned, showing that various texture, there are composite texture. In one surface itself we have two different kind of texture in A1, A2, A3 and A4 also. There are different size, and this is a nested texture. We texture inside a texture, texture inside a texture, and this is what I was mentioning. Instead of going for this kind of grooves, if we are able to make blocking this grooves, this is arrangement which will really give a good results to us. So we block it, we don't really allow it to the lubricant to squeeze out. So this is what we call a texture with a different structural feature combined in a nested manner. That's what we really require. And quite a time people have used MOS2 deposition in a nested structure and got a very good result. So this is possible also. I'm just showing one figure where we have tried with gear, this texture of the gears. We can see here there are number of textured the grooves, or maybe say pockets, and in these pockets, whereas we are assuming that there will be some sort of debris that will be generated during the rolling action, or the rolling sliding action of the gears, and that will get dumped into this. So this is a possible, utilizing this kind of texture we get a better results. Finally, I am going to show one case study when people have tried to generate a texture on a surface. You can see here the workpiece which is getting which is having a texture. Now here that there is a tool which is able to generate the surface texture, and this is a surface texture which you are able to see over here. Now here in this case they have done two motions. One is a 16.3 kilohertz frequency been given to this unit, while another one low frequency has been given to the holding unit also. They tried aluminum alloy against steel, and aluminum alloy, the texture and the overall chemical composition has been shown, and we are picking up this from one the published paper, effect of the micro dimple geometry on tribological characteristics of the texture surface, which was published in 2020. Now what they did after doing generating the texture, they really tested on a tribometer. That's what we are saying, commercial tribometer for friction test has been utilized, and then they use a partial, or we say starved lubrication condition. They use ISO VG68. That's what centi-stroke viscosity 68 centi-stroke, and they run this aluminum, this cylinder, against a steel block. Of course, after doing this, they did a necessary thing to remove the debris from with acetone and dry up, and then finally show the results. And then they found particularly that even they can generate a this is Strybeck curve, and because of the, when they supply more oil, supply lesser oil, they can generate a boundary condition, EHL condition, and hydrodynamic condition. So they can generate all kind of condition. However, we are just showing only for the staff condition, and they tried a different kind of dimples. You can see the 210 micron dimple, 217, 224, 225, 227. Coming to the depth, you can see here the depth is a 14, 15, 16, 16, 17, and then this they have done a different kind of the cases, and they say they have used the word case 1, case 2, case 3, case 4, case 5 to find out which one will be very useful. And there is another and the thing which I mentioned, that they go ahead with the density of the surface structure, and they have capped in this case 15 to 20%. One other literature say 11% density is optimal. We should not go beyond that, because after that we get a worse performance. I am showing the results of this paper only. You can see here, if the load is low, 10 Newton, even what they are showing the coefficient of friction for the untextured surface is better. So again, the texturing when we do, it is really important. If it is already in a hydrodynamic condition, or if it is already in a EHL condition, and we may not require a texturing. But if it is in dry condition, mixed lubricant condition, then we want to transit from that lubrication condition to EHL, to hydrodynamic, then only really required. So this is very important. So that's why I say that when the load is increased to 15 Newton, we are able to see that this untextured surface gives a worse performance. All other textured surfaces are giving better performance compared to this. In this case particularly, the case 2 is showing the best performance, while in this case 3 is showing the best performance. So the different condition, different kind of textured the dimension are showing the good or bad performance of the results in this case. So that was only for the friction. Now coming to the specific wear rate, You can see here they have used for the 10 Newton, they have used for the 15 Newton, and in this case they are showing able to see that this wear performance in case of low load and high load, in the both the cases the case 5 is giving the better performance. The deeper and more dimension of the texture feature is giving the better performance. So this is important. Now we are getting good performance of one texture dimension for friction, but other we and for other case we are getting other one. That means friction optimization we get a one kind of texture, for wear optimization we are getting other kind of texture. So finally we really need to go ahead with a multi-object optimization, which we have learned in lecture 10th also, that we really require that way. It is not a one feature will give everything. So either we go ahead the composite or go with hierarchical. At some few places we have one kind of dimension, some cases we have other kind of dimension. Maybe say that we overall required 11%, 6% goes to a low dimension, and 5% go in a higher dimension. That is need to be investigated the case to case. It is not a common case as such. So that's very important for us to understand. Now there is a huge literature, many papers are there. I'm just trying to show here particularly for coefficient of friction and stainless steel, and they have mentioned the optimal density. You can optimal density of the this surface structure, you can say varying from 8.5% to 25% cemented carbide, again 5% to 24.47%. So we have a lot of literature available on the this texture surfaces, and they are able to show that every case the coefficient of friction is coming down. The same thing happens to every case, the wear rate is coming down. So you can see here wear life has improved by 70%, wear width has dropped by 70%, wear rate has dropped by 65%. Under different load condition we are getting this kind of results. So in literature it very clearly says surface modification, surface treatment really improves the performance. So apart from a lubricant, grease selection, surface modification technique also needs to be done. And of course there is a huge literature available, and as I mentioned in the current days we are talking more about the surface texturing. If surface texturing is done, it may give good results. However, the cost is also consideration, because most of the texturing processes are costlier and they further require super finish operation. Now there is a kind of a thinking whether improving the surface roughness or optimizing the surface roughness can do the job of the surface texture, and that is what the future research will really show the results. By just doing the improving the surface roughness, can we get a same thing what we are getting from a surface texture. With this I'll try to close the lecture. Thank you for your attention. Thank you.